you all to start working on your project. I encourage you to come next time with questions. With these projects that you're doing, you have to write the code yourself, and you can't look at other people's code. You can talk about stuff. I'm entirely open to people talking about the projects. In fact, I'd encourage you to use the course mailing list, even, to talk about the projects. And class, because you can ask questions and I don't have to write back emails, so that's easy. But yeah, I encourage people to I don't know, he's got some important call or important music or something. I encourage people to talk about the projects to make them easier. And that means you have to start it. Because if you don't start it, you don't know what the problems are, and you can't get help. And that's unfortunate for everybody, mostly for you. So, yes, LLVM. We'll get to that after slicing. Everybody's back, so let's move on. So we talked about program dependence graphs and dynamic dependence graphs, and they tend to be really, really big. The problem with static program dependence graphs is that just because of the approximations that you make for potential dependencies that could exist in some execution, you have a lot of edges, right? If one instruction could depend on 5 others, then you've got 5 edges. And so the graph is very, very large. With dynamic dependence graphs, you have a problem where you have huge traces, right? Maybe gigabytes large, and there may not be a whole lot of dependencies at any one time, but there are a lot of dependencies in total, and they add up. And again, it complicates things. It's just difficult to wade through. So how can we start to deal with these things more reasonably? The underlying solution in general is called slicing. So a slice of a value v at a statement s, and this is traditional definition here, is a set of statements involved in computing v's value at s. What does that mean? Well, okay. We come down here, we've got a print statement. We printed out I. This is our same summing example we saw before. We're printing out the value I. And the slice is just a set of statements involved in computing I, or the slice of I at this point, rather. It's just a set of values involved in computing I. So we've got 7 is in the slice of itself, and it depends on the value computed here, or the value computed here, depending on which one gets used. And the value computed here depends on, again, it should be I is less than n, depends on this condition. So 2, 3, 4, and 7 are in the slice of I at 7, right? So it's really just the statements that may influence that value. It's a more informal way of saying it. If you could rip these statements out and run them on their own, ideally you get the same value. Technically that's not always true. It's a notion of executable slice versus non-executable slice, but intuitively, if we stripped out just these red lines and ran them on their own, you'd be computing the same value.
I have a question. So like line 4, if it's executed, that means that line 3 also executed. So,
yes.
So that's like redundancy. I mean, like, can you remove the line 3 and you just say 2, 4, and 7 are responsible? Or
in the representation of your slice, you might decide to do that. Okay. But ultimately, if you're looking at, there are other reasons for including this statement. So maybe you know that I is directly dependent upon 4 and 2, and so you don't need to hold on to 3, but maybe an actual bug that propagated down through your execution, maybe the bug was actually at 3, and it then gave some incorrect value to 4, which then gave some incorrect value to 7. So the transitivity is important. That's why we want to capture that. This notion of this transitive flow of influence is useful for tracking backward through the behavior, or even potential behavior of a program. And especially if you're looking at debugging, or if you're looking at something security related, especially security related, well, you don't want to just capture a potential information leak that starts here. You want to capture a potential information leak that starts anywhere with a broadcast value. Yeah. Okay. Reasonable enough?
Yeah.
Okay, so it's the set of statements that may influence V. So we have data dependence, we have control dependence. It's pretty clearly computed then using the program dependence graph, right? That seems pretty straightforward. And it's used in all sorts of things, right? Debugging, testing, reverse engineering, optimization, design profiling, malware analysis, basically anything you want to do. These notions of dependencies and slicing probably come into play at some level. If nothing else, for trimming down what parts of a program you want to look at, slicing is really useful. So how are we going to do this? Well, it's really a transitive closure of edges in the program dependence graph, starting at your slice criterion, whatever that initial value is. Okay, so we start from V and just follow the edges backward. That's it. So we're down here with I. Well, what is our program dependence graph? It's this messy thing, right? And you can see I've got the control flow edges in gray here. I've got control dependencies in red. And then I've got these data dependencies in blue. You can see why this is incomprehensible, right? So hopefully the slice makes it easier. Maybe not perfect, but it makes it easier to understand what's going on. So we're finding the slice from 7 again. We'll traverse backward along our data dependence. Notice we don't really have any control dependencies here. We're always going to execute 7. So we'll just go backward along our data dependence. And where are our data dependencies? Yeah, it's tough to see here. But the program representation, we can see 2 edges coming out here. The representation of the program dependence graph will say, I have 2 predecessors, and it knows exactly which one. You can't see it, but in the graph representation, it's easy for a computer to pick out. Yeah, it's 4 and 2, right? Because those are the potential definitions of I. And then from this one, well, we control depend on 3, right? And so these are our, well, this is, oh, did I stop there? Yeah, technically this is everything. What actually happens? Well, if you're at this point, now that we've added 3, well then at this point you have I equals I plus 1. What does this depend on? Well, it depends on 2, and it depends on 3, and it depends on itself in terms of its value, right? So no matter how much more we traverse these edges backward, we hit the same things. So we've hit a fixed point. And this means we've got the transitive closure, right? So this is really everything. Ignore the edges at this point, I guess. These are just the ones we actually traversed. But we've computed the slice as being 7, 4, 3, and 2, which is exactly what we said before, right? Okay. There are several different ways that you can do slicing. You can have static slicing versus dynamic slicing, program dependence graph versus the dynamic dependence graph. You can have backward versus forward slices. You can have executable versus non-executable slices. Sometimes when you rip the slice out of the program, you can actually execute that code you ripped out. Sometimes you can't, depending on what techniques you use. And you can actually have slices that are based on the edges versus slices based on the nodes. Sometimes I actually care about exactly which edges could be traversed. And I wouldn't just want to stop here saying I've got these statements and traversed these green edges. I'd actually want to know that 4 depends on itself. So I'd include that edge in my slice, depending on what your problem is. What would forward and backward slices mean? We saw a backward slice, right? What sort of a question could it answer?
Which statements were executed to get particular value?
Essentially, yeah. Which statements, well, in what we saw as static slice, it's not were executed, but could be executed essentially to get a particular value. Yeah. Or another way of framing that is which statements can influence a particular value.
Yeah.
What's a forward slice then?
Then it's opposite. This value, this statement, what can influence
Right.
afterwards.
Exactly, exactly. So depending on the direction, you're going to answer a different question. If you have a forward slice, what can this statement influence? Exactly. Any ideas why a slice might not be executable?
Unreachable code in the program.
Um,
No?
Undefined variable, I mean, the variable you're using, like sum, it doesn't occur in a slice.
Essentially that is an underlying influencing factor on this.
Why?
It gets some notion almost of not capturing all the dependencies that are necessary. So if you're not capturing, we showed data dependencies and we showed control dependencies, but there might be something else in there that's actually relevant, that affects the behavior of the program. And that can happen.
Like you had while I is less than n, there could be some pointer somewhere which is influencing, which is not there in code.
Hopefully we would capture that using our points to relationship. We'd be conservative and say, well, we could depend on this. There are some notions of slicing that are tied more to the structure of code versus the semantics, and those can really fall prey to these sorts of things.
So now if there are like lots of statements above which are actually giving the value to n, like they are data dependent on n, but we are looking for I, so we might not capture that, right?
You should transitively, so let's say n is a variable, not a constant, then if n depends on something, then when you traverse backward to this statement and say that the value of I here control depends on this, then all of the dependencies for n will also come into play, and you'll have to traverse those as well. What we're showing here is a very semantic structural view of a slice. Sometimes the lexical structure gets in the way. So when you say, if I have, there we go, the red ones that don't really, can you actually see the red?
Yeah.
Okay. If I strip out just these lines, sometimes that won't actually compile. And it has to do with the structure of the code, the lexical structure getting in the way of the slice, the semantics. It is usually possible to actually lower this representation to new code that is executable, but that's messy too. Okay. What do nodes capture?
Statements.
Well, they capture essentially the statements, right? They capture what could execute or what was executed, I guess, in the dynamic sense. Edges capture something else, right?
Control.
Or data dependence. They capture the actual influence involved. So you can say, well, here's what happened or what could happen, and here's why or how, based on the edges. You have richer information. So depending on what you want to do, we use different information inside that slice. Okay, so the strengths of static slicing, well, you're considering all possible executions, so it's necessary for something that's conserved. If you care about security, then often you'll care about a static slice, because you'll want to ask, well, what are the ways in which I could do something or could do something that is insecure, right? Might I leak secret information? They're faster to compute, and they're space efficient because you just have the program size. You had to be able to compile the program, so you must have been able to hold the representation at some point. The problems here, however, are that we have these ambiguities again. You've got multiple program paths, one path in this direction, one path in this direction, and so if we ask, what could A depend upon? Well, maybe it's this value, maybe it's that value, and really A depends on something in foo, so all of foo gets brought into the mix. A could depend on something in bar, so all of bar gets brought into the mix, and they end up including most of a program in the end, and including a lot of dependencies. This is because the transitive closure tends to be pretty expensive. And we also have these pointers, right? Aliasing is a big problem for static slicing because the ambiguity means you have to be conservative and say, well, P could alias P1, P3 could alias P2, and so we have to consider the dependencies on both of them. And again, transitively, it explodes. And similarly, you've got function pointers. You have to consider all the possible call targets. Pointers are a big problem. So if we consider dynamic slicing, this is really good for answering questions like, did I do something? So we don't have any imprecision from aliasing or from multiple program paths. Why is this true?
Because you are tracing it from
You take one particular instance, so
Yeah, there's no ambiguity because if you see a particular pointer, you know what it points to. You know what it pointed to at exactly that time in that execution. So this lack of ambiguity means it's very, very precise. They tend to cover fewer static program statements because of that precision. Because you don't have to worry about, well, this function pointer could have pointed to 5 different functions. No, it pointed to one, and you know which one that was. The problems, however, are that traces and computing dynamic dependence graphs can be pretty expensive. If you're capturing a trace of a modern program, that's easily gigabytes, right? It's a lot of information. They can also be slow to compute. This is because you churn a great deal of memory as you do this transitive closure over a graph that is gigabytes large. So this is expensive, or traditionally expensive. There are more ways around that, but it's traditionally tough. And we have very many statement instances and dynamic dependencies to examine because, again, the graph is so large. It's all about scale. It's really all about scale. And you also miss these alternative histories. You can't answer any of these questions like what would have happened if. So, maybe you had one execution and it took a particular branch and behaved a certain way. And you're really interested in, well, if this program had taken the other branch, what would have happened? You can't answer that sort of question at all because you only have the exact one history that you observed. Okay. So both of these techniques end up having problems of scale, right? Static slicing includes too much of a program, and dynamic slicing just has so many statement instances and has these traces that are huge. It's difficult to go through them.
But they might be repetitive because of, say, a for loop which is executing 100 times. You could just make blocks of them and you know that what is happening exactly. Like it might be easy to evaluate after that.
So the underlying issue, though, is that with the, I think this is with the static?
With the dynamic. Like in a dynamic trace, if you have for I less than 100 and 2 statements, they will be repeated 100 times. So you can make a block out of them and you would know that they are like similar things which are being repeated.
In that case, yes. So if you
and
have
just look at the corner cases, like when it started.
Right, so what you're describing are compression techniques, essentially. And compression techniques are what make dynamic slicing possible at all in a realistic scenario. They are used extensively in the practical real-world implementations. They're still not enough for a lot of real-world programs because the scale is so large. Compression is what's necessary to make it possible at all. I don't presently have any of those papers that look at compression techniques used in dynamic slicing, but we can do that too, if you're interested. Okay, so the question is, how do we prune things? How do we focus on things? And how do we use compressed representations? But we're glossing over that. So we have things like thin slicing, which focuses on propagating this original value and ignoring transference of this value through data structures. Right? Maybe data structure reorganization as you add more values isn't important. You just care, oh, this was added to the data structure, and later it was seen in the data structure or removed from the data structure. If a tree needs to be rebalanced, you don't care about all that internal stuff going on in the meantime. Not relevant. with things like chopping, which combine forward slicing and backward slicing, find their intersection, find out what's relevant. And look, things like confidence analysis. Maybe if you look at the structure of a graph, maybe if you look at data from multiple executions, you can build up some probabilities about different instructions actually having some meaningful influence on your dependencies. And so you can rank the probability of an actual dependence being relevant inside your slice. You can also have guided browsers that look at the structure of a slice and say, well, you know what? I don't have to show the whole slice at once. I can keep things nicely packed up, just show the slice for the main function, and if the developer says they want to zoom in on foo, we can zoom in on foo. No reason to show the whole thing at once. And in fact, maybe I can help guide the developer through which dependencies are there, so that I never show all the dependencies. I just ask the developer what's relevant, and we gradually build that slice together. Okay, and much, much more, yes. So that's everything we want to talk about with slicing. Now we can start to talk about LVM. Good, I think we have plenty of time.